Okay, folks, we are back. We are back. All right. I always hope it's with a bang. Hey. Now, in simplifying circuits, in simplifying especially expressions, Boolean equations and stuff, in solving them, sometimes you really need to understand Boolean, what call this, Boolean algebra, the rules. You need to, certain times, knowing certain rules is actually the can be the difference between coming unstuck or suffering miserably. So let's see if you can look at, there's quite a few, so we're going to look at what I would call the rules. This is for simplifying circuits. Alright, let's just say the rules. Let's say Boolean algebra. And then we're going to what? We're going to have, I'll just start with the rules. Alright, now let's start with simple things. What I'll do is I'll also, sometimes when you put a picture is worth 1,000 words, they say. So what I'll do is I'll also explain some of the things where I can use pictures, where I can use math that is simple. We'll obviously use that. We'll see to do whatever is best at any given time. Let's start with, if you add nothing to a what? To a variable. Alright, a plus 0. This is obviously a. But remember that this is what? This is binary arithmetic. Let's suppose we use a switch to, we've used switches before. So in our switch equivalent circuits, let's suppose our A was this switch, and then we say O. An O circuit is actually what? We said it's parallel. It's a parallel circuit. So O, 0. 0 means a broken line. Okay. A, or a break. Alright. So if our power is supposed to use what? If our logic depends on what? On A or a break. Obviously, this break is forever useless. Alright, the only determinant there whether there will be power or not is A. So if you have A or nothing, obviously the O is therefore a useless part. We might as well not have it because that line will never work. So this output here will depend only on A. Alright, that makes sense. Alright, let's look at A. Alternative to the thing, as an alternative to the open circuit, let's have a short circuit. Let's have A or 1. In this case, it's a permanently closed line. 1 is a permanently closed line. It's no longer 0, which was an open. It's a 1. Now, O is still a what? O is still a parallel set. So if you look at this now, it does not matter what the state of the state of A is. Whether A is open or closed, this line is closed anyway. So this is basically a closed line. Alright. Those are the first rules, and I'll call this the what? I'll call these two the identity rules. Okay. These are the identity rules. Alright. Now, I can therefore remove that and go to other rules. Now let's see if we then say, all right, these identity rules, these are the identity for O. I'm not done with the identity rules. These are identity rules for O, but we also have identity rules for what? For the end. So it's still the same. A and 0, A and 1. Now you can see that this is obviously what, remember, and once you see a 0, our output is 0. In an AND gate, if you see a 0, you know the output is going to be 0. Okay, mathematically we know that this is what, anything times 1 is obviously 1. But let's prove it with the switch equivalent circuit. There we have our switch A, but this time now A is in series with an open. Will there ever be power going through here? This is an open line. You can only get a current flowing if it's possible to close that line. If the circuit is closed, how can the circuit ever be closed if there's what? If there's an open. So this is as good as a redundant and useless switch. So our output is therefore that. Now, if however we said that was closed, for this second case here, if we say that was closed, a and 1, like just like it's a times 1 was a 1, in this case here, a and 1, you can see that this, what I do here. I said a times 1, I've been saying a times 1 the whole time. Can't be drunk this early. Juice doesn't get people drunk, does it? It's actually supposed to be a. I don't know what I've been thinking. Alright, a times 1 is not 1. A times 1 is what? Is a. So in this case here, you can see that this switch here only depends on what? Only depends on the a. If a is open, then the output cannot have power. The output will be off. If a is closed, then the output will be what? Will be energized. So you can see that it all this the whole this is basically the same as only having a. The control here is just a. That mistake probably, I hope people were screaming at me, you know. I hope people were screaming. It's actually quite early in the morning to be making such mistakes. Right, now let's look at a scenario where we have a with a. All right, let's start with what? With the o. A or a. Now, a or a, probably I should have started with end because I already have an end thing there. An end setup, remember end is a what? End is a series setup. Now, if we have a or a, really what it means here is that it's it's one switch. What it means here is that it's one switch. Why? Whatever happens, I might as well even remove this. I might as well even remove that because and make it look like one switch because they go together. If a is closed, both lines are closed. If a is open, both lines are open. So you can see it's as good as having one switch here. Okay, the other switch is basically wasted because now I could have used that switch for another circuit, but if I'm using it in the same circuit, in one circuit, I'm wiring both. If closing here is literally closing them. Okay, so it's as good as having only a. Okay, let me look at, before I go ahead, let's look at a scenario like this. Let's say, or let me go back there. Let me say this was something like that. I'm trying to clear it out. Right, let's say I had something like this where I have a permanently closed switch with another closed switch. So what is this? A 1 or 1. Alright, what I'm saying here is 1 is parallel to another closed switch. Okay, this is basically what is as good as 1. Okay, 1 or 1, 1 or 1. This reminds us of what? Of our truth table, the count 3, and what was our output? Our output was 1. Remember when we had a, b, and with 0 0 0 1 1 0 and 1 1, we know that as long as we see a 1 with an OR gate, we know our output is what? Okay, let's look out for 1s so they can be 1s. Otherwise, if they don't see a 1, then the output is 0. So we are looking basically at that scenario here. 1 or 1 simply means that scenario we know for an OR gate that output is 1. So I could even use a truth table that we should be familiar with at this stage to actually answer something like that. So now, if I wanted to look at this, I could have said maybe I can factorize here and say that becomes 1 or 1. If that is 1 or 1, we know from our truth table that 1 or 1 becomes what? I'm dealing with this scenario here. 1 or 1 becomes what? That, and for the OR gate, we know that gives us a 1. Now it takes us to what? To number 4 here. 1, 2, 3, 4. Number 4 here, where we already said that is the same as A. Alright, so it's just me basically trying to use different ways to have people probably visualize things. Like I said, the picture is worth 1,000 words. How we arrive at some of these conclusions, it's actually very straightforward. It's not the most complex. It is not rocket science, definitely. Alright, so if we look at the next possibility, there is we've had A or A, and then we can now look at what? At A by A. I always do the equivalent of the what, the end equivalent of whatever I do. All right, A or an A is equal to, now, well, it would have been A squared, wouldn't it? But let's suppose A was a 0. Let's take it to table. Let's suppose A was a 0. That would be 0 and 0. Okay. And then let's suppose if we were to use switches and say these are two switches, but they have one control, so that they're like the same switch, so it's A or A. All right, so if I close here, that definitely closes as well. All right, if I open, so whether it's open or closed here only depends on the status of A. If I leave A open, the whole line is open. If I close A, everything closes. So you can see it's as good as what, as having only A. Okay, so now if I were to probably say mathematically A or and A is the same as, if I factorize that, it's A. If I factorize that, so it does not really, if I try to use mathematics, it does not really give us a K. It's not as the previous cases where I could actually have I could have probably explained it mathematically. So here in this case, I think it will be easy to see with the switch. If I show you, if you can see that if you close here, we automatically close there. If you open here, then you can understand why it's as if it's actually one switch. All right, so we'll proceed and say, okay, we have something that is like A or anything else for that matter with this on inverse. Let's say A or not A. All right, if you look at this, if we take the switch and you say this is A, and you say or parallel to A but the opposite of A, what are we saying here? We are saying that we have a switch that has one control, but it controls two lines. All right, so now if I leave it B, if my switch A is on 0, that line is open, that line is closed, our output is 1. Okay, if A is on 0, the output is going to be what? Is going to get power, so our output is going to be 1. If A is on 1, what's going to happen here? If A is on 1, I'm pressing the switch. What do? I'm closing that line. Yes, I may be opening this one, I may be breaking this one, but I'm closing that line there. So again, it's a closed line. Again, it's 1. Okay, so what are we saying here? We are saying that A or not A is simply equal to a permanently closed switch. It's as good as a what? A switch that is closed all the time. Now, if we then say the opposite of this one here would be, the alternative to that one there could have been A and not A. Now we have a switch like this and one control, so it's one switch, but the other line is closed. What do? If we leave it B, if we have A on 0, we leave it B, that side is broken, so power cannot go through. Our output cannot be on. All right, now if we close this, if we press the switch, we close there, we take A to 1, but that is the effect of breaking that one there, so our output is still going to be 0 regardless. So this A and not A is actually what? Two conflicting switches. So therefore two conflicting what call this what can I say? I would say they are opposites of each other, yet they have one control. So obviously when the one is on one state, the other one is on the opposite state, so there can never be any power going through here. All right, so I think a picture makes it all the more easier to see. Now if we look at how many do we have so far, 2, 4, 6, 8, let's look at number 9. We have done this before. We have done this one before. We've said that the opposite of the opposite, double negation, actually falls away. Okay, well, I used an example where we said, remember I made an example with and O, And I said, okay, suppose we have an and, okay, the opposite of the and is equivalent to the NAND. Okay, to the NAND. The opposite of the AND is equivalent to the NAND. Now we then said, but we know that the opposite of the opposite is obviously the original. Ne? So now if we say the opposite of NAND, if the NAND is the opposite of AND, then obviously the AND is the opposite of what? Of NAND. So what does it mean? This here is the same as what? As the opposite of NAND, which is the AND. Now, these two statements, what do they mean? It means, therefore, we have the opposite of the NAND, okay? I will not put it like that. I will put it like this, and I will say, but this is equivalent to my NAND, and the opposite of that is therefore the AND. Okay, the AND. If I put it in a what call this? In a statement, what did I say? I would have said here A and B. Okay, A and B, the opposite is the NAND. And I'll say here the opposite of the NAND, if I put it in a statement, the opposite of the NAND, A and B. Why do we talk of A's and B's without having A's and B's? Let's just put A's and B's. Let's just put A's and B's to probably not lose some people. Okay. Alright. Alright. So now the opposite of the NAND. Okay. Here we said, okay, let me make this a little bit, because it's a little bit difficult to do there, but here it's easy to say A and B, because that's what it is here, right? But because these two are almost the same thing, so if I say the opposite of what, the opposite of that is obviously is here I'm saying if you invert the end, and however it looks the same, that's why probably it looks stupid to do it twice like that. But this is the NAND gate, here is the end and the not. Okay, so I don't know, it's a little bit funny without being funny. Now if you look at this one here, we are saying if we have an AND, this is an AND gate, not a NAND gate. This is the inverter, and we are saying, that's why we rewrote this thing here. Okay, what we did was split this into two gates. All right, so this is the inverter, and then the inverter of the inverted output. This is the inverted output being inverted again, and it took us where? To there. So all I've done this before. I've done this before. I'm just probably doing it for what? For emphasis. That double negation is as good as what? Is as good as redundant. All right. So probably took longer than I should have here, considering that it has been done before. Let's then look at other. All right, let's name these rules here. Okay, what I would probably call this here, I'd probably call these two here. I'll probably call these two here, would call them, very big word, ne? Idempotent. Idempotent. Some say idempotent, others say idempotent. Does not matter. I mean, you have a topic on algebra on idempotence, so it's a huge topic actually. All right, now, then obviously if you look at this, these are inverses of each other. If you multiply the inverses, you're going to get a 0. If you add the inverses, so these are inverse rules. Okay, these are idempotent rules. Those were idempotent rules. These are inverse rules. All right, probably these are all rules anyway. I don't know whether I should be tautological and keep repeating the rules. All right, this one here is the double negation or double complement. All right, this is double negation. This one is the double negation. Not that people have to really fuss about the names as such. You need to know how to use them usually, more than you need to remember what they are called. Okay, double negation. Okay, or since we know that this is what we've dealt with what we called, you can also call it diable. Remember, we've been doing complements, complements, complements. We've been doing this as complements. All right, so we can call the diable negation or the double complement rule. All right, so we then have other rules though. We would have something like, let's say we have something like A or AB. For me, these would be derived rules. Why? If you look at this, I mean, it's straightforward that let's just do mathematics here. This is the same as what? This is the same as A into, like doing math now, we're actually basically factorizing 1 or B. Okay, if I number these rules, let's say for some reason I want to number them so that it's easy for me to point out to a specific rule that I'll be applying at any given time. All right, if I look at rule, for instance, rule 2, this here according to rule 2 is the same as 1. Okay, and this here according to rule 4 is the same as A. Okay, so I think people can see therefore where it comes from. I don't know whether I'll have enough space if I keep doing things like, let me try to keep it there and thing. So now let's say A or not A, B. Okay, it will be tough to explain this. Let's say I had here a what? A scenario. Let me try to use remember this is what? If I use a picture, which I've claimed is worth 1,000 words. If I say this is A, then I come and I say we have said that O means what? Means a parallel set, but the end part means an end set. So if we do this, this is one switch. Basically, I don't even need to name the other one because I've shown that it's one thing. So if A is open, it will be open also the side. So there's no way power can pass. Ne? If A is closed, it doesn't even matter what B is. So if A is open, there's no power. If A is closed, there's power. So it doesn't really even matter what B is. That's why this one does not care about what? About. It was easy to do the maths. It was easy to do the maths and factorize there. It's so difficult to do the maths here. But if you use the same thinking that we can use switches, it's A here, then it's the same scenario. We have an O and an end. So this here is A, but that is the opposite of A. Okay, that is the opposite of A, and this here is B. Now you can see if A is open there, that line is definitely closed, and we depend on B. If A is open, if A is not activated, that side is what? Is open. That side is what? Is closed. So power is waiting there anyway. It's waiting for B. So this time around, B is going to decide what's happening. Or if we close A, then it doesn't matter what B is. So these two depend on that, on either B. When you don't care about A, you will worry about B. Or if you don't care about B, if where B is not important, A can still do the job. Okay, so but A being open does not say power will go through. It will depend on B. But when we activate A, now we do depend on what? We don't care about B. So both of them are equally what? Are equally important. So therefore, that helps us therefore to what? To the picture actually solve that for us, and we can now come and conclusively say this here can fall away. So what are we saying here? We are basically saying in any scenario Z or not Z with N something else, C will mean that can fall away. X or not X, Y, for instance, that will fall away. As long as it's a variable, remember, it also means not X or x, y, it means that one will follow as long as the one or the inverse of, in fact, let me just call it the one. Let's say this one and its inverse with something else. No, not and. Or its inverse with something else. Then that inverse will fall away. So it's not about the inverse always falling away. Sometimes if I can come here and say not A or A, B, that A will fall away. Okay, the inverse that is with the end will fall away. All right, so it's very important to actually highlight that what has just happened then. I did not do that. It is artificial intelligence being artificially unintelligent. So we'll go to the next one and say, okay, let's see, we can have A or into A or B. All right, here we can do the maths here. You can do the maths. If you look at the maths, this here is going to be equal to A, we're expanding here, AA or AB. Now, that rule there is rule number 6. And we know that rule number 6 gives us A or AB. Now, we remember that if it's A or, we haven't done this one, have we? No, we haven't done this one. I feel we should have done this one earlier. Okay, we haven't done this one. All right, what this is if we take out, no, we haven't done something like this, have we? A or AB. No, we have here. We have here. All right, this we have here. So this is going to be what? Let's probably number them further. Number 10, number 11, and number 12. So according to rule 10, we know already that this is just A. What does this mean? We didn't really explain this. Let's suppose we have A and you see yourself, you are going with A, B, C. You see yourself, you are going with A, Z. You are going with, you see yourself with A, not Z, Y, for instance. As long as it's A or anything with A in an end state, okay, all those can fall away. Why? When you factorize, it's going to be 1 or all those things. 1 or anything will give us 1. All right, it's very important that I should come back and highlight that as well. All right, okay, so now probably I should now number them. I've seen how it's important to number them in case I need to refer to them later. Now this here will be, because you can see things are being absorbed into the what? Into the brackets here. We are actually using absorption. We are actually using absorption here, okay? So therefore these are absorption rules. Like I said, it's not really that important to be naming these things. Like it's not, as long as we know how to use them. All right, so I'm going to look at another one that I would call, let's say we've got A or B into A with something else, C. All right, mathematically speaking, A times A, AA, okay, or A times C, AC, or A times B, AB. Oh, this is already getting familiar. Now that's what? BC. All right, so now what that means is that this is A, okay, that there is, if you are going to look at rule what? It was rule A, that was rule 6, and then you look at, that is AC, that is AB, that is BC. All right, now if you look at this, this is now going to what? To rule 10. That will fall off, that will fall off, and will be left there with what? With A or BC. And now there's nothing that you can do with that. Okay, what have we done here? We this will be called what? The distributive. We send the distributive law. Okay, so we go to rule 14. I was praying that I'll have enough space. I don't know. I have a few left. Now, A and B not. Now this is what? This is coming from De Morgan. We can break the rule. Let's see where it comes from. Not A. I'm breaking the line. What is going on? I'm having my pen going berserk. Now I'm breaking the pen, so this will be times, but I broke the line, and this will be B. All I've done is break the line here. So what is it telling you? It's telling you that not A, yes, not and anymore. So if it's not and, it's what? O. We are saying change the sign, okay? And then not B. Alright, so this here is basically De Morgan's theorem, alright? And then also it obviously applies with what? With the addition as well. We've done the multiplication. Now we're gonna do this is going to be break the line. The sign must change. That is our broken line, the remainder of our broken line. So we change the sign, not this sign. So it's A, not what call this O anymore. So and it's what have we done here? These two are De Morgan's theorem. So De Morgan was indirectly a student of what? Of Boole. Ne? De Morgan's theorem was derived from playing around with Boole, alright, with Boolean laws. So these are what? These are our, well, I'll call them 15 for now. If something else comes up that I probably forgot, I'll come back to it. But I think I've demonstrated how we arrive at each and every one of them where I could. I've used whatever means was necessary to get to show why we are saying whatever we are saying. These rules are very handy. Every time you get stuck when you are solving things, look back to this table and you will see that your solution will come from one of these rules here. All right, thanks. I hope that was more tantalizing. I hope this was more what people like. All right then, ciao.